Okay, perfect. Welcome to our third online class. Thank you for making time to join. For those who are joining with their personal accounts, please next time join using your student emails. I think I've accepted a few people in the lobby. I'm just trying to avoid stopping and pausing as the lesson continues. It's kind of distracting. So please make sure that next time you join with your student account. Just a sec. Sorry about that. I had to open. So this is our third online class, as I was saying. I think so. Okay. So that's me there on the picture. For those who are joining us for the first time, and to the usuals, welcome back. I usually like it when there's a lot of people. I can see today there's a lot of attendance. So yeah, thank you so much for making time. So please, I beg you once again, do contact me for assistance with the module content. Don't wait for the latest day or day before the assessment. As you study along, whatever you do not understand, do make sure you contact me. I'm available on emails so that you're able to continue understanding the material as you flow with it. So this thing of waiting for the last minute, you get confused and sometimes you miss a lot of things. So I'm very much available to assist you with this module. So please do make use of that opportunity. So that's my availability. Do drop me an email. I'll get back to you and assist you. And then, so for today, you should know by now what we would be doing because I've shared with you, I think in the first welcome session, I shared with you the study plan to say at least each week do something. So we said already that time that when we meet, we already know what we'll be doing in terms of the content that we'll be covering, the feedback that we'll be getting, and also what we need to prepare for in terms of the coming assessment. So this is what we're going to look at. It's a brief feedback. So I won't dwell much on it now because I've given you a detailed one on the announcement. So if you do not understand anything on that one, please do contact me. And then we'll do a preparation for assessment 3. By preparation, I mean we're going to go through the learning units that will be covered in assessment 3. Who's this? Please make sure that your mics are mute. I don't see who it is. Thank you. Okay. So that's what we'll be covering today. And in terms of assessment plan, if we've done assessment 1 and 2, and then please note that for assessment 3, it was supposed to open, I think, on the 22nd, if I'm not mistaken, which was yesterday. So I've shifted that. It's going to open on the 29th. No. I'm mistaken this with another one. It's actually going to open on the, wait, let me see. I think it's day after tomorrow. Yes, day. So it's going to open on Friday and then it will close on Friday, the 3rd of July. So I'll just change this when I send the slides. I think I just took a different one, but it was supposed to be due on the 29th because it was going to open, I think, on the 21st, 22nd, somewhere there. But I've shifted that, but you still have the same amount of days that I usually give you. So I usually give you a week. So if I open it on a Monday, it's going to close the following Monday. So this time around, instead of Monday, it's opening on Friday, then it's going to close the following Friday, meaning it's going to open on the 26th and close on the 3rd. Are we clear on that? You still have the same amount of days. Are we clear? Are we happy? I hope it won't inconvenience any of you. For those who are working shifts, you have at least a day off in between in that week. So you'll make use of that time. So I did mention that we're going to cover learning unit 3 and 4. With 1, usually it's just the definitions and concepts that are attached to. So in this case, it would be the definition and concepts that are attached to learning units 3 and 4. So it doesn't necessarily mean that you'll go back and read assessment 1, but we're trying to assess your understanding of the definitions and the concepts that are linked to these specific learning units. Sure. I think my battery is dying here. I need to change this battery. Okay. Excuse me. So in terms of the feedback, who of you have seen the announcement that I posted? Just by a show of hands. Did you go through it at least? See, there's like 3 people. 4. Okay. Is it helpful? Is it helpful for me to do those kind of feedbacks? You can unmute it. Just
yes, it's quite informative.
Okay.
Yeah, it's not that it's like script based, but it's honestly it's like a memorandum, if you can say that. So yeah, it's appreciated. Yeah.
Okay, I'm not supposed to give you a memorandum. It means that I need to tone it down. But I'm just trying to make you understand where you're going wrong. So while I was marking, I noticed that most of you, it's not that you do not understand. I think there's an issue of sign conventions in most cases, because I think it was question 2, if I'm not mistaken, where if you got your sign conventions wrong, everything else would be wrong, because now you're using those those values as negative instead of positive, or as positive instead of negative. So you get a different answer. Although you're following the correct steps, but if you miss your signs in terms of sign conventions for stresses, then you're gone. That's why in the previous classes, I always said that if you grab this, you're done. If you grab this, you're done. So that's what I meant. I guess now you understand. Does that come through, please? Okay, I don't see on the other side who's unmute. Oh, okay, I see. Okay, they muted now. All right, so yes, that's one thing that I picked up. It's not that you don't know what to do, it's just the issue of sign conventions. That was the main problem. And then the other one was with the diagrams. There was poor performance in the diagrams. Those diagrams that you needed to draw, yeah, it was poorly performed. I mean, usually when you draw, remember you're doing an engineering qualification, right? There's simple things that you shouldn't miss out marks on. Let me do this. For instance, if I'm drawing this cube, I want to show you the stresses, right? I cannot just say I'm pointing like this, and then say, for instance, I say this is 50 megapascals. What does this mean? I need to have a simple Cartesian plane. This would be my X. This would be my Y. You already have marks to show that you have this understanding of saying, okay, I'm not just drawing this part, but this is engineering. Put that in the background. Okay, I need to understand that, okay, this stress is acting on this block, so it's on the y-axis. You need to be able to define or to identify what it is. So by missing simple marks, I mean, if you can just draw this without showing me that this is y, this is x, you've missed out marks from just showing that it's y and x. And then one other issue is that compression and tension. People are still confusing that. we said compression. If you're drawing a compression, it needs to show that it's pressing onto the box or onto the plane, right? And then with tension, your arrow must show that it's going away. So some people were not sure. You'd find that someone drew an arrow like this. It has both, it's showing up and down. What am I supposed to do in this case? It shows that you're not confident with what you're doing or what you're saying. So you need to make sure that you understand. And then with your shear stresses, we said shear X parallel to the plane. Is it going to cause a clockwise rotation, or is it going to cause an anti-clockwise rotation? If a shear stress is drawn like this, in this case, this is going to cause a clockwise rotation. What does this mean? It means that it should be positive. If it's facing upwards, it means that it's going to cause anti-clockwise rotation and it's going to be negative. So there's two things with clockwise and anti-clockwise rotation. It's the shear stress, which is your tau, and it's the theta. They're different. So with the tau, which is the shear stress, if it causes clockwise rotation, it's going to be positive. Now with your angle, we said we measure an angle from the x-axis. If we from the x-axis, if we go anti-clockwise, that's where it's positive, right? That's where it's positive. So if I'm from the x-axis going this direction, it means that my angle is going to be negative, negative value. So those are the things that, those are the things that people were struggling with. And once you understand these concepts, you are done. You are done. So what else? Okay, with this one, it was just a matter of, if you do not understand these sign conventions, then yes, you would use the correct, you would use the correct formulas, but your answers would be wrong because your input values are wrong. And then, okay, diagrams I did mention. Then this here speaks to the stress elements, which also everything basically touches on what I've just discussed here. Is there anyone with a question before I move on? Going once? Going twice? So, okay. So I take it that you all understand. Do you all understand? Why is it quiet? Okay.
Yeah, yes, for me, I don't understand, ma'am.
Okay, perfect. Thank you. So I was very disappointed with the performance of the class. Even the moderators did mention that it's the first time we have such a performance. It's just that I can't open it here now. But even the external and internal moderators are stating that there's poor performance in terms of what I've just explained now, which is your sign conventions and also with the diagrams. In some cases, some people didn't even answer all the questions. And you cannot expect to get, sorry, you cannot expect to get a pass if you're not answering all the questions. I mean, what happens if whatever you've answered does not even amount to 50% of the question paper? Do you expect to pass? Definitely not. So please make sure you attempt each and every question. I mean, there's few marks that in some cases I was allocating 0.5 marks to people who you could see that this person is trying to answer a question. They could jot down something, but yeah, it's almost there, but not yet there. But you could see that at least they attempted. So for someone who did not attempt at all, it's very difficult for you to even give a 0.5 mark. So yeah, the performance is really not good. It means that because if you look at the numbers here with the first assessment, so this is assessment 1, and then this is assessment 2. So with the first assessment, a lot of people also submitted, although it was not the whole class, but a lot of people submitted and then it dropped with the second assessment. And also with the pass rate, I think maybe because you're writing at home, you have the whole week to do the assessment. A lot of people did perform very well. But then with this one, now that it's timed and you need to show that you understand, yeah, it's quite tricky. Only 50 people passed, so you can imagine out of 114 people, 50 people pass. It means all of those who did not pass should now write assessment 6. Assessment 6 is a must for you guys. So of the 50 who passed, so far you do not have to write assessment 6. So assessment 6 is more like a supplementary, if you take it that way. It's more like you're trying to redeem yourself because you didn't do well in the previous assessment. Are we happy? Are we together? Can we go to the actual content of the day?
Yes, ma'am.
Ma'am, can I ask a question before you continue?
Yes.
Yeah, I wanted to know if there's any way where you can see the scripts, our scripts, we can see them and then see where is our weaknesses so we can push hard on it.
Unfortunately, I'm not allowed to share the major test scripts. It's treated more like your exams. Remember, you would write your assessment back then. It would be assessment and then exams. With exams, I don't know how it's done. I don't want to lie, but I'm not allowed to share those scripts. So that's why I opt to give you that detailed feedback. So with the detailed feedback, I expect you to take now your script that you submitted, you take the detailed feedback that I've given you, try to make comparison to say, okay, maybe I got this one, maybe I didn't get this one. Then you could perhaps get a better understanding of how well you did or how bad you did. But I'm not allowed to share those scripts, unfortunately.
So, ma'am, you can't even share the memorandum.
No. That as well, I'm not allowed to share.
Okay.
So that kind of feedback, usually a lot of lecturers will not even go to that far to give you detailed feedback like that. So I'm just trying to have you to understand where you went wrong and then just make a comparison. Unfortunately, I'm not allowed to do that.
Yeah, ma'am, but it's a bit challenging because we might think we got this, but the results when they come back, it's something else.
Mhm.
So yeah, that's why it's challenging. I see the detailed review and all of that, but yeah, it's still challenging because we still don't know what am I good with the signed conventions or do I need the theory more or what's going on?
Yeah, unfortunately, I cannot share the memo and also the scripts. It's out of my office. It's out of my control. I just don't know who you can take it up with. Maybe from assignment department. I'm not sure. I'm not sure in that one. I don't want to lie.
Okay, thank you, ma'am.
Okay, I saw a hand. Yes.
Thank
Who is
you,
it?
ma'am.
Yes.
Just to help on Rehan's, when you go to your assessment, on your assessment platform where you can see your marks, there is a tab. There is a tab that is written review. You can click on that one. It can show you your script.
No, it doesn't. That's why I'm asking from her side.
It doesn't
Oh.
show the script. They blocked
I
it.
think
It
the one
shows
that
the-
you can see would be the minor assessment. Remember, it's 2 platforms that you write on. The
Oh,
minor
on the
assessments.
major assessment, ma'am, on the major assessment, it wasn't showing, but I just checked now. It does show. Maybe you can check
Mine
after the
is
class.
also showing.
Okay, then that's good. If it shows, then everyone should be able to see it. Because also
Just go
on
now
this-
and check because I also open it now and it's showing.
yeah, someone said it's visible also on the chat. So I think that's good. That's good news that you are able to see them.
Okay, ma'am, I have a question. I think you've already mentioned this before, but I just want to get clarity on it.
Yes.
Are we able, since you can't give us the script or the memorandum, and sometimes the view thing on the assessment info doesn't allow us to see the scripts, is it possible for us to kind of like screenshot a part of the question, our answer script that we think we might have gotten wrong, but we are not sure, just like the diagram where we had to draw? Is it possible for us to email you that part and then you would kind of like give us the corrections on it or clarity on where we went wrong specifically?
Sure, that would be like I'm sharing parts of the memorandum with you. I think what you could do is to try and have a similar question, not exactly that one, but a similar question, or but not, I don't want to get myself in trouble and get you guys in trouble as well. But it shouldn't be the exact question, or it can be something along that line, but it shouldn't be the exact thing where you like screenshotting and then I screenshot on my side. I mean, it's gonna come back to me sharing the whole memorandum. Imagine student A screenshots question 1, student B question 2. So it's gonna come back to me giving you the actual memorandum.
Okay,
I don't know
thank
if
you.
I'm making sense.
You make sense. Thank you.
Yeah. Okay. Any other question before we move forward? Twaki. Yeah.
Yes, good afternoon, ma'am.
Afternoon.
Just a question, not a question, actually a request.
Mhm.
Could you please share the example questions similar to that one for the diagrams, especially the Morse cycles, because the one that we had in the major test, it was a little bit difficult because of the information that was given and the time on top of that. So can you please share examples, more examples on that one, so that we'll be able to practice and see if we can be able to overcome the challenge that we are having?
Okay. I'll see how to do that. But in the meantime, I think you should also do the discussion forums, because there's questions in the discussion forums that will help you practice the content. But I will also work on the examples. And also maybe just for noting is that the module now is under what? Not development, but we are trying to refine it so that we add more examples. So it's being modified in terms of adding a lot of examples in the learning unit itself. Like for learning unit 1, you'll get specific added examples. So that's what we're busy with.
Okay, thank you.
I've noted your request.
Okay, thank you.
Okay. Can I move forward now?
Okay, ma'am, last one.
Yes.
When it comes to the Morse cycles, if you draw it out of scale, is it fine? As long as you know your points. Because it's time consuming having to find it scale and having to draw a perfect circle.
Okay. I wouldn't say it's fine, because now people are going to cheat. Instead of drawing the actual and reading off from the actual diagram, what you would do now is go to calculate, and then you come and draw a perfect circle, and then you just put your points there, which is now pointless. So maybe what I can do, or maybe what you can do, is to, if you're one who writes with your hand, it's best to have a graph paper maybe printed out before the day of the test. So you know that, okay, you won't have to figure out a lot of things in terms of scale, because with the graph paper, it's much easier as opposed to when you're writing on your actual book. So for those who write, use Microsoft Word or whatever, I will try and have a graph paper attached on the question paper at the end. Is that fine?
I'm not.
Sorry, ma'am, can I please ask?
Yeah.
Are you gonna attach the graph paper on the question paper for the exam or for the assignment?
Well, if there's a question that would need you to draw a Morse cycle, what I'm saying is I'll then attach a graph paper. So for those who need to, who use their hands to write, then you print out. It means that if it's a major test where it's timed, you should already have a printed out graph paper.
Oh, okay. Okay, ma'am.
Yeah.
All right.
Okay. Let's move forward now. Okay, so again, learning unit 3 comes back. I guess this time around you will redeem yourselves. So it's still, I haven't added a lot of things on these slides, but it's still the same content. So let's go through it. Learning unit 3 is strain analysis in 2 dimensions. Remember learning unit 2, we did stress analysis in 2 dimensions. So now it's strain. But whatever we do in terms of strain, it does apply or it stems from what we were taught in learning unit 2, which is the stress analysis. So we again have our sign conventions. Okay, the state of strain at a point underground, or yeah. But you know that if you have an object and then you apply stress, your result would be strain, isn't it? Strain is the change in shape or length of that object as opposed to how it was initially before the stress was applied. So strain is the result of stress, okay? So we still have the same equations where there's transformation. Remember, in this module we said if we have our angle theta, we reference it to the x-axis. If we're measuring it that direction, what does it mean? What does it mean? I want to measure my angle. Say this is the point I'm interested in. I want to measure this angle there. What does this mean? Is it going to be a positive angle or a negative angle? We start there. And it's quiet. Oh, come on, guys.
It's gonna be a negative angle
Why is it negative?
because it's going counterclockwise.
We're going counterclockwise. We said it's not negative, it's supposed to be positive. For this module, right? Here's my x-axis. If I'm measuring an angle from the x-axis, if I'm going anti-clockwise direction, my angle is going to be positive. Right? So you are confusing it with the shear stress. We said shear stress acts parallel to the plane. So it's acting parallel to this y plane. If it's going like this, it's going to cause a clockwise rotation. This is positive. So don't confuse the two. With the angle from x, that side, positive. Are we clear?
Yes.
Okay. So with the angle, don't get confused. Your angle is positive when you measure it from the x-axis going anti-clockwise. It can be called anti-clockwise, counterclockwise, whichever, but if you're going counterclockwise from the point of reference, it's going to be positive. If you go clockwise from the point of reference, it's negative. That's your angle. Okay? So that still applies when we're talking about strain. It's the same with strain and with stress. And then with principal strains as well, you have your equations. I'll give you the formula sheet for the timed assessment. So there's no need to stress about that. What you need to stress about is your angle and your strains or your stresses. Your stresses, you stress about your stresses. So this is just in a nutshell what strain analysis is all about, right? So this is the outcome and assessment criteria that you should know. If one did not do well in test 1 and do well in test 2 and have a mark above 50, is it a must to write test 3? Not really, but you You should write. It's not a must, but you should write because already you failed test 1. It means that you are able to at least improve your mark, but it's not a must. Okay. And then with the outcomes, I think this doesn't change. Just go and read it and know. This kind of tells you what you'll be tested on. So what I was saying earlier on, when you apply stress on an object, what you will get is strain. In this case, do you see this? This here, what does this mean? I'll just pick Khunsi. Yeah. Matlala. What does this mean? You have your object and you have this force facing that side. What does this mean? Khunsi? Okay, anyone to try it?
Ma'am, I don't get your question.
Okay.
Are you asking us what the force is?
Yes, I'm asking you. You see these forces
Tensile.
that I've put, it's tensile. What does it mean in terms
It's
of your
stretching.
magnitudes? Come
It's
again?
being pulled.
It's being pulled. And then if you're given that this force is say 20 kilonewtons, what does it mean when you're writing it or when you substitute it into an equation? What's the sign convention there?
Is it a negative?
Perfect. It's going to be negative. So whenever you see, whenever you see diagrams, that's where you should start actually. Or if you read a scenario and you hear they're saying tension, just try and have a diagram like this, and then you draw your forces to say, oh, okay, this force is tension. It means that it's pointing outwards, it's stretching. You start there before you go to the equations. So you try and understand the scenario. If you're given a scenario, you try and understand it by trying and drawing a diagram like this to see where your forces or your stresses are acting. So in this case, it's tension, it's pulling it outward. It means that it's going to stretch in the y-axis. If this is my y-axis, and that's my x-axis. So it means that it's going to be pulled, and then it's going to be thin here. It's going to be thin. So what happens here, this dotted line is the initial shape of the object, and then that force was applied, then it stretches and then it becomes thin. So that stretching and the reducing of the width there, that's your strain. So strain, we look at it in 2 directions. So it's the axial and the lateral. Okay, it's the axial and the lateral. And now there's also shear strain. Remember, when you apply shear strain, it's parallel to that plane that it's being applied on. So it means that there's going to be sliding. That's why you see that now this shape has changed from being a rectangle like this to it moved a bit diagonally. So what informs your strain? Now with strain, you look in terms of sign conventions. You look at the bottom left corner. You look at the bottom left corner to say, is it narrowing or is it opening up wide? If it's narrowing, then it's going to be negative. If this corner here is narrowing, can you look at this diagram here and look at this? Can you see that initially, yes, it was at 90 degrees, but now it's no longer 90, it's less than 90. Then it means that it's narrowing, then it's going to be negative. That's your shear strain. Okay. So we know compression, we know tension, and then we know the shear strain. So people, one other thing that I picked up, people are writing Y instead of gamma. These two are different. So your shear strain is gamma. This is not Y, it's gamma, right? So you should write it as gamma. It's more like an R, but yeah, it's gamma. Don't confuse the two. So it's not Y, it's gamma. So this is what we need to know here. It's the shortening and the lengthening, and also the widening and the narrowing. So these two, they speak to one item. These two, they also speak to one item. Which item is this? This is the normal part. The normal part, remember we said normal is perpendicular to the plane, And then this is the shear part. The shear part, we said it's parallel to the plane. Okay. So that is what we're looking at. Now, this is still what we're talking about. We said normal stress, it's going to give you a normal strain. So it's the change in length or change in width of that object. That's your normal strain. And then shear stress, it's going to be your change in angle. So that's what I was talking about. Is it narrowing or is it widening? So your gamma, it's the narrowing and widening. Your epsilon is the shortening and the widening, lengthening, and the stretching and the shortening of the object. So these are the two things that we look at. That's the strain, the effect of stress. So it depends on the kind of stress that is applied. The normal stress, meaning that if I'm applying a stress where I'm compressing the object, or I'm applying a stress that I'm pulling the object, what I will get is either shortening or lengthening. So that's the normal stress. Normal stress, you're going to get lengthening and shortening. Shear stress, you're going to get widening and narrowing of the bottom left corner. Okay, remember we're doing 2D in this case, so we usually represent our stresses in a square or rectangular object. So don't be scared now that we're talking about the bottom left corner. What about a circle because it doesn't have a corner? No, we're only going to look at these kind of shapes where you'll have your bottom left corner. So don't stress about that. So this is just an example of you that I wanted you to understand what strain is. So you just imagine yourself holding a sponge that has water. So when you squeeze it, your squeezing is you applying force or you applying stress to it. And then the deformation of that sponge. So when it shrinks or when it starts removing that water, when the water drips, of course, it's going to change shape and then it's going to be a bit, it's going to, depending on how big your hand is, it's going to form a bit of a ball or something like that. But the squeezing or the distortion of that object or the sponge, that's what strain is. It's changing shape, right? Because of the load that you're applying or the stress that you're applying on it. So that's basically what happens on the rock. So when the stress is applied on it, it's going to change shape. Of course, you might not notice it visually instantly, but you'll see the effects. So I'll show you just now. You only get to see the effects later on of this applied load. So again, strain transformation, these are the key equations that you need to know. Remember, we said in this module, what do we do with our theta? Can I get Colin to answer this one? What do we do with our theta? I need to make sure that you all understand this. Colin? Oh, guys. Okay, Nomfundo. Pumelele. Can I hear from you? Oh, guys, can I hear from, let's see, Blessed? If you guys are quiet, then I'll just call it a day and then we stop.
Mom, can you please repeat the question?
Okay, I'm presenting you with these equations. It's for strain transformation. So with strain transformation, we mean that the object is being transformed at an angle. So I want you to explain to me what you would do with this angle theta. What does it mean? What do we do with it in this case? When is it positive? When is it negative? I want someone to explain that to us. When is it positive and when is it negative?
Is it positive when it's measured clockwise?
Yes, who's talking? Mabetlela. Oh, sorry for butchering your names, guys. Yes, come through.
I don't really understand the topic, but I remember reading somewhere that it's positive when measured clockwise.
Okay. No, it's not positive when measured clockwise.
Okay.
I explained this earlier on. And who was it? Who, yes, come through, Tswaki?
When it's anti-clockwise, it's positive, and clockwise, negative.
Okay, but you should give reference to where you're measuring it from, right?
Okay, from the x-axis, when it's anti-clockwise,
Mhm.
basically against the clock, it's positive.
Mhm.
And then from the x-axis going down from clockwise, basically, so it's going to be negative
Yes, yes,
from the
that's what I
horizontal
wanted.
point.
Yes, perfect. That's what I wanted. So I need you to understand if I'm to just say, okay, tell me what would happen if you have a compression and a tensile force or stress. You should be able to know, like, from your heart. You shouldn't go back to the learning unit to say, is it positive, is it negative? This is something that you need for this module. These are the things that you need to know. These are the go-to things that you need to know so that you are able to answer whatever question that comes your way. Okay, so I just wanted to test if you really understood what I mentioned earlier on, because we did have this question not so long ago. So because now when you have to use these equations, you would need to know, is my theta positive or negative? Is my strain positive or negative? Is my, this is the normal strain. Remember, the epsilon is the normal strain, and then the gamma is the shear strain. So is my normal strain positive or negative? What informs that? Is there a shortening or a lengthening? Do you remember? Do you recall from the previous slide? So shortening, it's positive, which is weird because you would expect that if it's shortening, then it should be negative. No, you know why? We have a lot of we take compression. I think, yeah, this was part of something that was asked in your test. So in mining, remember, there's a lot of if you look at the environment that we're in mining, the most common stresses or forces that we get are compressive. So for us to avoid having a lot of negative values as we're working with the calculations, it was decided that we will use compression as positive and then tension as negative. That's how it is with rock engineering, rock mechanics. So that's the main thing. The most common ones are compression. Not that we do not have tension, we do have, but the most common ones. So imagine if the most common ones we were to work with, it's going to be negative. Everything would be negative. It's just going to be chaos. So to simplify things, we have a lot of compression, then we use those as positive. So okay, and then with your with the shear strain, so you need to know, if you find it positive, it means that, oh, okay, it was because there's widening of the left corner. But if you find it negative, you should know that it's because there's narrowing of the bottom left corner. So that's what it means. So even if you're not given a diagram, but you're just given values to say, okay, there's epsilon x, say it's 30. Okay, these ones usually I like 10 minus 3, so it would be 0.3. Okay, yes, but then yeah, you have your epsilon x, it's say 30, and then epsilon y, it's let's just say negative 20. So it means that okay, this one is positive. What has happened? You ask yourself. I mean, when you are presented with your epsilon and then you see this different signages, what happened? What does this mean? Let's go back here. Okay, remember, shortening and lengthening are speaking to epsilon. Widening and narrowing are speaking to your gamma. Okay, if you get a positive epsilon, it means that there was shortening somewhere. right? It means it's an effect of compressive stress. So let's go back to what I was talking about now. Which one is positive? Which one is negative? Okay, the epsilon x is positive. It's an effect of compressive stress. So if I'm to give you these values and ask you, okay, what stress was involved here for you to get this kind of strain? It should be a compressive stress. Why? Because compressive stress, it makes that object shorter where it's being applied. So if you're on the x-axis, if you're applying compressive stress on the x-axis, so this is x, that's y. Remember, this is the plane of x. So if you're applying it there, this thing is going to be shorter, right? Remember, it should be equilibrium. So it's being applied on this side and on that side as well. So it's going to be shorter, then it would result on an epsilon, a positive epsilon. If it's tension that it's being applied, so it's being pulled away, then it's going to stretch. And when it stretches, then you're going to get a negative value for your epsilon. So that's what you need to know. If you are given whatever values, when you look at their signages, you should know, okay, this is a result of compression, this is a result of tension. Also with this shear strain, if you are given a positive or a negative, you should know it's because of widening or shortening of that bottom left corner. Okay, I hope you're not confused. I hope you're all clear. Are we happy? Are we clear?
Ma'am, can I please ask you something? So when
Yes.
we check these equations that you are sharing now, we need to go back to the slide that you shared before. We need to determine if I don't know what that is, but that thing that looks like a Y. We need to determine if it's
gamma.
positive or negative and be able to tell, or the gamma. Yes, we
Yes.
need to be able to tell if the gamma is positive or negative. Then we will be able to tell if there's compression being applied or tension being applied on the object. Is that what you're saying to us?
Okay, what I'm saying is, okay, you partially got it, but your last statement now it's a bit, I'm a bit worried that you do not understand. So with the compression and tension, compression and tension, it speaks to your epsilons, right? Epsilons, this is the normal strain. Remember, normal is perpendicular to the object. So your normal can be compression where you're pressing onto the object. It can be tension where you're pressing away or you're pulling outside the object. So your compression is positive. Your tension is negative. So this is for stress. Again, with strain. Remember, the compressive stress is going to shorten your object in this direction where it's being applied. Meaning that your epsilon, if you find it positive, it's a result of this kind of stress. Your epsilon, if you find it negative, it's a result of this kind of tension. Then with the gamma speaks to your shear stress. Remember the one that acts parallel to your plane where it causes sliding, right? So that sliding there that we are talking about, that's why we look at the bottom left corner of that object to say, is it narrowing or is it widening? So don't confuse the two. So basically, if we're to compare stress and strain, right? Your stress, remember, it's sigma, and then your strain is epsilon. So these ones, sigma, remember we have sigma y and sigma x, but in your sigma, we speak about compression and tension. Also with your epsilon, which is the strain, we speak of lengthening and shortening. Why do we speak of lengthening and shortening? It's because of compression and tension. It's the compressing and the pulling away. So when you pull your object, it's going to lengthen. And then when you compress the object, it's going to shorten. So these are the two that speaks to normal stress and normal, these two, they speak to normal. So it's your normal stress and your normal strain. And under these two, it's two. Under each of these, there's two, which is your compression and tension. And now the other one is the shear. So with stress, your shear is your tau, and then with strain, your shear is your gamma, right? So we look at this, it's acting parallel to the object. If it's acting parallel to the object and then it causes clockwise rotation, it's positive. This is with stress. And then with your gamma, if it shortens at the bottom, if it narrows on the bottom left corner, it's going to be negative. If it widens, it's going to be positive. Are we together? Are we together? Do you understand now? I didn't get who was asking that question. And I don't know if you're still here, but I hope you do understand now. Can I move forward? I'm looking at time now and we still have to do learning unit 4. Guys, are we happy with what I've just explained now? Hello?
Yes, ma'am.
Okay, I see a thumbs up. Okay, fine. There was actually an example that I wanted us to do, but I think due to time, you'll just do it on your own. But you can see, you are given this information. What we were talking about, you look at the signages. Okay, it's sigma x. Let's look at sigma x. We said your epsilon speaks to sigma. With sigma, we're talking about the normal stress. So it's acting perpendicular. So we can see that this is positive. What does positive epsilon mean? A positive strain, it means that it's due to compression, isn't it? Remember, with stress, when you compress an object, it's positive. Also with strain, the result of that compression, it's positive, which is shortening. Now, we look at epsilon y, it's positive, which means it's also the same. Now, your gamma xy, it's negative. What does this mean? It means that the shear strain that was acting there, it caused that object to narrow at the bottom left corner. That's why it's negative. Remember, narrowing at the bottom left corner, it's negative. Widening at the bottom left corner, it's positive. So when you look at these, when you look at these numbers, you should already be able to tell those things. And then your theta now, it's positive. What does a positive theta mean? It means that if you're measuring it from the x-axis, going that side, it's positive. So that's what it means. Anti-clockwise, counterclockwise, it's positive. So what do you do now? You are required to calculate the strain transformation. You just go back now to the equation, to these equations. You know this one is positive. You know this one is positive. This one is negative, and that one is positive. So your thetas, you know all these things now. You're confident enough to say, okay, I'm gonna get the right answer because I'm sure of my sign conventions. Then you plug it in there, you get your answer. To prove that you have your answer right, then you compare your answers, your epsilon x and y to the epsilon x and y. So epsilon x prime and epsilon y prime, you compare them to the ones that you were given. They should be exactly the same. So if you get another one saying negative and another one saying positive, then you know it's not correct. They should all have the same signage to show that it's correct. So please go and do this example. Yeah, I won't dwell much on it. And then let's move forward. I hope we are clear, né? And then again, with the principal orientation, principal strains, you use now the same information that you got. This same information that you got, you use it to plug it in these equations. Then these are the equations that I'm talking about, which are your principal strain equations. You knew from what you were given earlier on, okay, epsilon x is positive, epsilon y is positive, this is positive, that's negative. If this is negative here, just put a bracket there to avoid getting a lot of distraction or confusion. So from the previous example, this was positive, this was positive, this was positive, this was positive, this was negative. So make sure that even when you punch it in your calculator, you do put in a negative, then you're good to go. And then with your principal angle, this is the 2 theta that you need to calculate. And maybe there's something that I picked up, and now I remember. When you were doing your more circles, right? Remember, you would have a circle there. Say, for instance, these are the 2 points that you would have. This angle that you measure, it's not theta, but 2 theta. So it's this angle here, it's 2 theta, not theta. So if you are to measure with your protractor here, what the value that you would get, say for instance, you've done this calculation and then you got your theta. Don't be surprised now to see this angle here, when you measure it, it's double this. It's because the measured angle here, it's 2 theta, not theta. Okay, that's when you're dealing with the Mohr circle. And then here, but this is just a plug and play. So if you have to calculate the maximum shear strain, and then this is the equation that you use, and then that is it. So I guess with this one, it's a plug and play. Once you understand this, you are able to answer your strain transformations, your principal strains, principal angle, the maximum shear strain. You are able to answer a lot of things. That's why when I mentioned earlier on to say, if you get your sign conventions wrong in the beginning, chances are the whole question would be wrong. So the only marks that maybe you would pick up is that you got a 0.5 to say you know which equation to use and stuff like that. But yeah, you should know your sign conventions. Okay. And then this here is just an exercise where I wanted you to do the principal strain calculations using the same these values or data that you've been given, but you'll do that at your own time. For those who want more examples, here's one. And then, yeah, this is just to explain. Remember what I was explaining just now? Can you see this is 2 theta? So this is 2 theta, not theta. So the angle there that you get. And then now the same thing applies. Let's take you were to draw a Mohr cycle of stress, not strain. Then you would be given your sigma x, you would be given your sigma y, and your tau xy. Right? Then you know on your y-axis you would have your tau, on your x-axis you would have your sigma. These things are still the same. The only difference is if now we're looking at the Mohr cycle of strain. With strain, remember sigma speaks to epsilon. So you have your epsilon x, you'll have your epsilon y, and then your gamma, whatever gamma you'd be given, it will be gamma xy. But when you plot the actual value, it should be divided by 2. That's the only difference. But the other steps are the same, exactly the same. The only difference is that with your gamma now, you just use half of the value that you're given. So in this case, that's why you see here, it's gamma xy over 2. Here there's no values, but I'm just trying to show you that this is what a Mohr cycle should look like. So already you know that you would have a mark here for you to know that you are able to identify where your gamma goes and where your epsilon goes. You have a mark there. There's 2 points that you need to plot, the 2 initial points that you need to plot, which will be your x, epsilon x is to gamma xy over 2. That's the first point. And then the second point will be epsilon y is to negative gamma xy over 2. So these points here, these are the second points that you need. That's a mark. That's a mark. Now, what do you read off after you've done this? You draw your perfect circle. You read off the maximum value here at the center of the circle. That's your gamma max over 2. So in calculation, yes, you might have calculated your gamma max here, but the one that you will get on the Mohr cycle, it's gamma x over 2. This value here that you would read off here. It's gamma x over 2. So if you have to tell me what gamma x is, then you would multiply this value by 2. Gamma max, I mean. And then the other points that you need to read off that are critical it's this one here. The one that touches the far left, far right of the x-axis, that's your major principal strain. And then the one that touches the far left, that's your minor principal strain. Then you measure this angle, that's another mark. You see, there's easy marks to get here. There's easy marks to get. So please make sure that you draw what is needed or what is required, and you plot and you show the values as well. So don't just put here a point and then that's it. You'll get nothing or half a mark. But you need to tell me, okay, this is your major principal strain, which is given by epsilon1. What's the value here, which is equal to XYZ? This is 2 theta, which is equal to XYZ. This is epsilon2, which is this much. This point here, it's this one you are given. This one you just divide by 2. Then you have that point. So I think what I saw when I was marking is that people are just using what's this? They just use the equations and then they know what these values are. And then they go ahead and just draw a perfect circle and then they just put a value there. It doesn't necessarily work out, because you'll find that the value that you put here, it doesn't match with the point that you're talking about. It doesn't, the two do not speak together. So what's on your Cartesian plane in terms of the values should also speak to that circle that you have. I should also be able to read off what you have. So if I'm to locate myself on this point and I find that it doesn't speak to what it should, then it's not the right one. Because I mean, your circle should be a perfect circle, meaning that the radius should be the same all over. And then when you put these points, I should be able to read off this value here and that value there, and they should speak to the value that you put here. The values in between should show that indeed what you have here is correct. It's not just a matter of going to the calculator, you punch in the numbers, and then you know what values are supposed to be here and there, and then you just draw a circle and then you put those values there. It doesn't work that way. Okay, so again, this is just part of what I was explaining there earlier on in the previous slide. So you step 1, there you have epsilon x, gamma xy over 2. The second point, sigma y negative gamma xy over 2. You connect the 2 points. So these are the 2 points that you would find. Remember, you draw your Cartesian plane, you have the values on the x, you have the values on the y-axis, which is your gamma and your epsilon. Then these are the 2 points that you'll get first. Then you draw a line where they meet here. That's your center. You read off that point there, and you know you have the values that are needed. So this is basically how you go about drawing a Morse circle. And then this example we did in the previous class, I won't dwell much on it. I see we are over time, but I think I'm just gonna stop at 5. Did I set it until 4:30 or until 5? Yeah, but I have another engagement at 5, so I'll just take it until 5. So let's go now to I think let's go to learning unit 4, because this example we've done before. So what you would do here now, you know, okay, epsilon x is negative. Oh, okay, now you ask yourself, what brought about this negative? Remember, compression is positive, tension is negative. It means that this thing has stretched. It's stretching of the object or lengthening of the object. That's why you see a negative. And then there you get your positive, meaning it's because of compression. And there you got your positive. It means that it's a widening of the bottom left corner. So that's why I was saying, when you look at these values, you should be able to speak to them, just like what I did just now. Then it means that what value are you going to plot at first? Your epsilon x, which is -5. So you're going to get your -5 is 2. Remember, gamma xy should be gamma xy over 2. So it's going to be -5 is to 6. And then the second point that you would plot now, it's going to be 6 is to -6, isn't it? Then you go ahead to connect the two. So -5 would be somewhere that side. So it's going to be something like that. It's to 6. And then 6 is to -6. So it's going to be something like that. You connect your values, draw your circle, you read off where they meet, you measure your angle. If you're measuring it from the x-axis going anti-clockwise, then you know it's your 2 theta. You read off this part, you read off that part, then you're good. Is it? Yeah, then you get something like this. So your -5 is to 6, there you got it. And then 6 is to -6, there you got it. Then you join the two, the angle that you measure is from the x-axis going anti-clockwise, you get a 2 theta. You can even measure it from the x-axis going clockwise, but you know if you're to give it and writing, it's going to be negative because it's clockwise. So if you're measuring it from here going anti-clockwise, it's going to be positive. And then, yeah, so this is basically what you need to do when it comes to Morse circle diagrams. I hope we are all good. And then maybe one last thing, just to show you, remember earlier on when I said you might not be able to see the strain effects on the spot, but these are some of the things that you get to see underground because of, remember, strain. When you apply stress on an object, it's going to deform, and when it's deforming, it's there's some sort of energy, which call it strain energy. So it's work being done. So that energy is stored. Remember, you cannot destroy energy. Energy is just it can only be transferred. So it gets stored, and then you only get to realize it a bit later. Also, because of the way we are mining, there's a lot of things that are involved when it comes to that strain energy that is being stored on the rock mass. So when it gets released violently, that's where you get to see your rock base underground. So there's an impact of these things. We're not just doing it with these diagrams for no reason. This is, of course, the basics, but as you gradually go up the steps in terms of rock mechanics, then you get to understand why you were doing all of these things. So how does the stored strain energy cause rock base? Remember, the main outcome of this strain energy when it gets released is rock base. So we try to make sure that the environment that we're working in, we try and minimize the possibilities of this rock base by the way we mine and the way we support and all of those things. So we know that, of course, when stress is applied on the rock, it's going to deform. But when it deforms, it's work being done. So there's going to be energy that is stored there. So, of course, also when we mine, remember the vibrations from the blasts, the drilling and whatever, we're disturbing the rock as well. It's just that, yes, it might be minimum at that time, but it gradually builds up that strain energy within the rock. So then the stresses that we're applying, it gets redistributed around the boundary of that excavation. And then sometimes you get that there's concentration, depending also on the shape of that excavation, there's going to be concentration at a specific point. And then later on, or as time goes, when that energy is too much, then it releases violently, then you get your rock bursts. So it's energy now being transferred. Now you're gonna, instead of it being static, you're gonna see your kinetic energy now with this rock burst. So you wouldn't want to find yourself underground when such things happen. Okay, let me switch and go to learning unit 4. It's mostly properties and behavior of underground rock. We've touched on the properties of rocks a bit earlier. I think in learning unit 1, we were talking about when you're testing a rock, what do you test for? And things like how the rock was formed. They all speak to the properties of the rock. So depending on how that rock was formed, what it has been subjected to, it's going to behave differently. also how far deep is it underground? It's going to develop, behave differently. So different mining environments would behave differently. So here we're trying to understand, okay, with these properties that we now know, how is the rock going to behave now when it's underground? We know it was formed maybe through magma, molten magma, cooling down and stuff like that. We know that formation, we know the different formations of the rocks, but now we need to understand how now is it going to behave in when we do our excavations, when we come in with the excavation. So this is what we're trying to understand in this learning unit. So we'll look at secular excavations and also compare them with rectangular excavations. So here it's just to show you that different, when you have your excavation, it's going to be affected differently based on, of course, the geological features that are there, the amount of stress that it's being subjected to. So there's going to be different failures or modes of failures depending on what is happening around that excavation. So this is just to show you some types of failures that you can get, but here this just depicts a stable excavation where there's no disturbances. Here you have a lot of geological disturbances, terms like your joints forming blocks, then you get your wedges. Here there's caving in. There's a lot of things, but don't bother much about this. I just wanted you to see that there's a lot of things involved that bring about different stability modes or failure modes of the excavation. So these two pictures here, they're just showing you, just try and zoom in. We have what we call isotropic and anisotropic. So these two, maybe you might have heard them somewhere. So the isotropic one, it means that you have the same strength all around, or you have the same stress all around. So doesn't matter if it's on your X or Y, it's the same. So a rock that is subjected to the same stresses in both sides. Remember, we're only looking at 2D for this module. It's going to behave differently from the one way maybe you have strongest stresses acting in this direction, and then as opposed to maybe this plane. So it's going to behave differently. We'll zoom into that. Where am I? We'll zoom into that a bit later. So this is the outcome and assessment criteria for learning unit 4. Please go read through it. I won't dwell much on it just because of time. But yeah, it doesn't change. It's always going to be like this. So this is what you guys need to do. And then these are the concepts. So the bold and black is what you need to do. And then the red is the concepts that you that speaks to what you need to do in that card. And then, yeah, like I was saying, the different mining environments. Here, we've just put in 3. There's shallow, intermediate, and deep. How do we differentiate them? Of course, by the depth at which they are located. Some of you who are working, you by now know where you fall under in terms of how deep is the mine that you're working on. Is it less than 1,000 meters? Is it between 1,000 and 2,250? Or is it beyond that? So there's also ultra deep, but I didn't put that in. We're just going to focus on these 3. So you need to know, okay, in terms of stress fracturing, what happens in these environments? How bad is it? How intense is it? In terms of stope closure, the rate at which when you advance per meter, there's closure at the back. Remember, that's why they have what we call supports like your backfill, your pegs, those kind of things. They're trying to minimize the closure. They're trying to look at the closure rate that comes with that kind of mining environment, more especially at deep and ultra deep mining environments. That's where you find a lot of closure happening in those stopes. And remember, those stopes are also very small. Some of them even less than 1 meter. So yeah, you can imagine. And then there's energy release rate. Remember, we were talking about the strain energy that was stored. It gets released at a rate. So we talk about that as well. You need to be able to compare these three different environments in terms of that. So we know that shallow, usually if you are to get failures, it would mostly be your faults of ground because it's mostly there's a lot of geological features like your joints that when they interact, they form a lot of blocks. And then because of gravity, of course, you get your falls of ground. It doesn't mean that there's no fall of ground in these other environments. It's there, but it's very strong in shallow mining environments as opposed to intermediate and deep. And then rock best as well. Where is it severe? Where is it minimal? You need to know all these things. So please look at this table as well. And then I think one other thing, yeah, these three are very important. You need to understand these three types of stresses, if I can put it that way. Virgin stress, we've touched much on this earlier on, where we know that your virgin stress is Q, given by rho GH. Your rho, it's the density, G, it's the gravitational acceleration, and then H, it's the depth or height. Yeah. So this is the stress that is there before we come. So before we come, it's stress that's originally there in the rock because of how deep it is. It has nothing to do with us. It was there, it will still be there. So it's natural. It's a natural kind of stress that exists. Depending on it increases as you go deeper in the surface. I mean, deeper underground from surface. And then there's what we call induced stress. So this is where we come in now. This is natural. This is because of us. So the more we drill, the more we excavate. Remember, there was stress there initially. So when we came, we are imposing even more stress. It means that the excavation that we are creating, there's going to be redistribution around it of the stresses. So it's our stresses and then the virgin stresses that will give you now the resultant stress. That's why you see that the resultant stress, it's a product of, or is made by virgin stress and induced stress. So it's the stress that was there originally before we came, and then we also came and added our own stress, meaning that we're going to get a resultant stress. It's just basic maths. So I think in that, this slide is basically speaking to the previous slide, where these are the equations now. How do you calculate your resultant stress? How do you calculate your induced stress? From this equation already, resultant stress, we have other equations of also that speaks to that. This one, it's the rho GH, and then induced stress, you can calculate induced stress also from this. You just make induced stress the subject of the formula, and then this goes to the other side, it becomes negative. So induced stress would be resultant stress minus the virgin stress. So basically, this is what you see here. So with the resultant stress, we use what we call the Ketch equations. We're gonna look at that just now. We use the Ketch equations, and then virgin stress, this is just the normal one. You just need to know the depth and the density of that rock. So yes, here again, you see angles, you see circles. So here, this here will inform how you use your Ketch equations. These are the Ketch equations. But remember, with whatever you have learned in learning unit 2 and 3, which speaks to the angle, it still applies here. Remember, if I'm saying I'm on the x-axis and that's the point of interest, how do I get to that point? It means that it's anti-clockwise. My theta is going to be positive. You see? Okay. So what happens now with the stress around circular openings? Please pay attention. When you have a circular opening, right? The stresses that you get on the skin of the excavation are going to be different from the stresses that you get around outside the excavation. So a circle has a radius, isn't it? So the radius of this circle is given by this R, big R, capital letter R. Whatever point of interest that you want to calculate it. So around, remember, okay, let me just do this. You have, let's just say you have this block of rock. It's a rock mass. And then you come, you put your excavation, your circular excavation here. So with these equations, what we can do is we can know what stress is here, what stress is there, any point around it. Doesn't matter which direction, at any point of interest, we can know the stresses. As long as we know how far it is, how far that point is from the center of the circle, and also in terms of the angle, how far is it? That's what we need to know. So it shouldn't confuse you. Interest is D. It means that my small r would be equal to the big R, because from O to D, it's the same as the radius, isn't it? Are we together? I'm running out of time, sure. But I hope you understand. So don't confuse the two, the big R and the small r. So the big R, it's the radius. And whatever point, if you are interested in a point along the skin of this excavation, so we're talking circular excavation in this case. If you're interested in that, it means that your small r and your big R are going to be the same. But if it's not the same, it means that your point is either it's going to be outside the circle. So if it's outside the circle, you know, let's take, for instance, here's your big R, and then let's say from A to B, it's 5 meters. And you are told to calculate the stresses here at point B. Then you need to know what is R at point B, your small r. Of course, your big R will not change if this excavation is still the same. What is small r now? Your small r would be from O to B. From O to B, you have to add. Remember, we said small r is from the center of the circle to the point of interest. So it's going to be R plus 5. It's the radius plus 5, isn't it? So that's where your point B is. That's why you see here, this is just, if the radius of the circle is given as 3.5, then you add your, this is just me giving examples of numbers so that you're able to know. And then from O to C, if it's just giving random numbers. But what I was trying to explain is that you know that your point of interest should be measured from the center of the circle to that point. So you shouldn't take it from the skin of the circle to the point. It should be from the center. So if you're only given, say you're given a scenario where they tell you that the diameter of the tunnel is this much, and then your point of interest, say it's at 5 meters from the skin of the excavation, you know that, okay, your point of interest, if you have to put that number in the equation, it should be from the center of the circle to the point of interest. So meaning that because you're given your diameter, you must find your radius first, which is the big R, and then you add it to that 5 that you're given to say the point of interest is at 5 meters from the skin of the excavation. Then you get your small r to that point of interest. Now, in terms of the angle, it's the same. If you're measuring it from the x-axis going anti-clockwise, it's positive. If it's from the x-axis going anti-clockwise, it's going to be negative. So those are the things that you need to know. How far is the point of interest? At what angle is the point of interest? Those are the two major things that you need to know here. And Zwaki, your hand is up.
Yes, ma'am. I just wanted to find out. So when we're answering the question regarding the the same method that you are saying. So are we going to include the distance and the angle to that point, or how are we going to answer it?
Radius, the small r, which is the distance from the center of the excavation to your point of interest. Also, the angle, theta, which is the angle to your point of interest. So you need to know these things. In this case, you have different angles. Point A is at angle 0. Point B also is still at angle 0. Point C is at angle theta. Point D is at angle 90. So the first thing that you see on these equations, okay, you have two sets, these ones. You have your radial and tangential. So the same way we were calculating, remember with the stresses, you are calculating your sigma x prime and y prime. In this case also, you have your radial and tangential stresses. So you see there's Q, which is your Wegener stress. That's why I put this equation first. So you need to first know your Wegener stress. Okay, how deep are you from surface? What's the density of that rock? Then depth is given by h, density by that, gravity 9.81. Okay, fine. Okay, what's the K? Remember K ratio, we mentioned it in learning unit 1 and 2. Your K ratio, which is the horizontal to vertical stress ratio. So you need to know that if you're not given, then maybe you might be given Q, which is the information that you will have to calculate this vertical Wegener stress, and perhaps you are also given your sigma H. So with sigma H and sigma V, you're able to calculate K, or you might be even given K. And then the other thing that you would have is the big R and the small r. Big R is the radius of the circle. The small r is the distance from the center of the excavation to your point of interest. So you use these equations. So once you know all these things, you just plug into your equation and then you get your answers. And then there's this equation here. The maximum tangential stress, it's given by sigma theta max. It's given by this equation only if it's a point along the skin of the excavation. Why? Remember at the point on the skin of the excavation, your big R is equal to your small r. If you input this where there's r, you equate it to the small r into this equation, this one. Remember, it's tangential stress. You'll come back to this. It's just mathematics. So to avoid doing all these long calculations, this is what you will use if it's on the skin of the excavation. So that's your tangential stress. Maximum tangential stress. Only if your point is here. So we can only use that equation in this case for point D and point A to calculate the tangential stress at this point. So you must take note. Are they saying you should calculate the tangential stress or the radial stress? Don't get confused. Tangential stress, it's sigma theta, and then radial stress, sigma r. Okay? So you should also understand, just go and play around with these equations. Right? Take a scenario where you have constant values of Q, R, and R. And then play around with K. Look at K when K is equal to 1. Look at K when K is less than 1. And look at K when K is greater than 1. What do you get? I want you to play around with that. Remember, K is this ratio, sigma H over sigma V. So look at the tangential stress when, so you're doing that for this second equation, not for the radial one, for this one. You want to look at the tangential stress at this point. Just look at what are the effects when your K is less than 1, when your K is 1, and when your K is greater than 1, but keeping all the other values and angles constant. The other things must be constant. Just play around with K and see what happens for you to understand the effect of the K ratio on excavations. So now we need to compare your square or rectangular excavation with the circular ones. With circular is that there's uniform distribution of the stresses. Remember, the radius is the same all over. So your stresses are redistributed evenly. But with the rectangle, the issue is the corners. You get very high stress concentrations on the corners. So that's why you see that in most cases, underground mining excavations, they try and run away from square excavations. If you look at the design of most tunnels underground, they are horseshoe shape, something like this. You look at them, you find they're trying to run away from these corners because they know it's dangerous. There's buildup of stresses here. So if you have such an excavation in your mine, just go and look what's happening here at the corners. What's happening at these corners? What's happening? So they're trying to have this. Yes, it might be cheaper and easy to excavate as opposed to the circular opening. I'm looking at the tunnel or a haulage. Then how they came about the horseshoe is because, okay, it's easier that way. Let's try and not have a sagging foot wall because we're going to have a collection of water here also. Then try to have it something like this. Then you have your kind of horseshoe. So, but the main reason is they're trying to run away from the buildup and concentration of stresses at the corners. So that's why you have your horseshoe, because of course circular was not working. It's not realistically perfect, except maybe when you're doing your shafts because it's going downwards. But with the haulages, it's something else. Okay. And then here we're just trying to compare your circular openings with rectangular openings. If you are to ask to compare, what would you say? With circular ones, the smooth flow because the radius is constant. So the redistribution around is even. And then with the rectangular ones, the issue is with the corners because there's a lot of buildup of stresses there. And then this is just something that I took a screenshot of on what software was this? I forgot, some rock science software. I think by then it was Experiment 2D, if I'm not mistaken, when I took this. But it's just trying to show you the buildup of stresses. Can you see this? This legend here, it's showing you that there's maximum stresses here where you find your red. That's why you see there's a buildup, change of the shade here. It's a bit going to the maximum sigma 1 because of the concentration of the stresses. And then here's another one which just showing you that there's high induced compressive stress, these corners. So the issue with the rectangle and the squares, it's the corners. So then there's also this part here where you just need to read up on. It's about comparing your stress-induced fractures with dilation. What are stress-induced fractures and how do they happen? You look at the brittle fracture of rock. How does a brittle fractured rock look like? And what kind of rocks usually can have that kind of failure? It's your granite, your quartz, etc. So what happens is that, for instance, when you go to the lab and you're testing your rocks, say you're testing your granite, the way it's gonna fail, you'll see that it's brittle. It's not just going to be along a specific failure plane where it's quiet. It's going to be a bit violent and it's going to have, in Venda we say like machaka chaka. I don't know what you call it in English, but there's like smaller pieces around, like if brittle rock breaks, it's not easy for you to put it back together and say this is how it broke. You just find, yeah, there's too much crumbs. Do you call them that? I don't know, but yeah, it's not like your perfect. I have to draw something. It's not like your perfect failure where you get something like this and then they say it fails. It's gonna be like this, and then there's gonna be like a lot of, some would even fall down. I'll try and find a picture so that I can put it here before I share the slides. And then you would also have the bottom part, but there's going to be like a lot of pieces in the floor. You can't easily put it back together. So also with dilation and buckling, the fractured rock now takes up that volume. Say it's on your excavation like this. This is where you're going to find your dilation and buckling. So in these cases, that's where you need to sometimes support your side walls and make sure that the support that you put there is active, not passive. So this is just part of what you need to know in terms of theory. And then, oh, okay, I think I'm done. And then also the comparison of the different shapes and also your calculations. Also, you need to know the effect of K on circular excavations. Play around with this one so that you'll be able to understand. If you play around with it, then you'll be able to understand it theoretically and explain it as well. So here, just know the angle theta. How far is your point of interest from the center of the circle? At what angle is it? And then the radius should not be confused with the distance to the point of interest. And then don't forget that this, you only use it when you are calculating the tangential stress on the skin of the excavation. So I think, yeah, I'll stop there late now for the next engagement that I have. So the next time that we meet online would be on the 3rd of August. But for now, just go through the recording, go through the slides when I send them. And then on Friday, your assessment will be open. So it's opening at 8 in the morning. Make sure you complete it, complete all the questions, and then you upload it before the due time. So that is it from my side. Apologies for taking 14 minutes of your time. Until we meet next time, it's bye for now.
Thank you, ma'am. Bye.
Thank you. Bye.
Thank you, ma'am.